Okay, here is a narrated answer key for the quiz on writing the free radical reaction products. And so we'll start with the first questions, which ask us to come up with a numerical value for the number of unique products. So in this case, I've got 1, 2, 3, 4, 5. I've got pentane. I'm going to rewrite this a little bit bigger. So I've got my pentane molecule, and the question is how many unique products do we get? So in this case, substitution at either of the CH3s would give me product A, which is going to be 1 chloro, chloropentane. Substitution at either of the two CH2s that are next to that is going to give me product B, which would turn out to be 2 chloropentane. And then finally the CH2 in the middle would give me product C, which would be 3 chloropentane. So in this case, there's 3 unique products, A, B, and C, that you would get from this reaction. So again, I'm using the idea that there's symmetry in this molecule, so that the CH3 gives the same product, the CH2s give the same product, as does the CH. So then for product C, or for problem number 2 here, I'm going to write out the structure. So how many unique products are here? Well, we've got these two CH3s would both give product A. And then the CH would give us product B, and the CH2 would give us product C. So if I'm writing product A, one of the things that I could do is I can actually draw this as a line bond structure. So there's product A. For product B, there's product B, the tertiary. Product C would be the CH2. Then this CH2, is it a different product? I don't know. Let's see. It is, because in this case it's going to be 1, 2 chloro 4 methylpentane versus 2 methyl 3 chloro pentane, so that's a new product D. And then the CH3 on the end would give us our last product, which would be 1 chloro 2, 3, 4 methyl pentane. So that would be product E. So in this case, we have a grand total of 5 unique products that would be formed in this reaction. Okay, and then for product C, or for question 3, there's actually a symmetry to this molecule, so that it turns out that all of the CH3s would give the same product, which I could call A. And so they would give, if I'm writing out the line bond structure, they would all give this product, which would be 1 chloro 2,3-dimethyl butane. So that would be product A. And so all of these CH3s are A's. And then the two CH2s would both give the same product, which would be 1 would be 2 chloro 2 methyl 2 chloro 2,3-dimethyl butane, which would be a new molecule. So in this case, there are 2 different products, and this kind of shows the symmetry this way and the symmetry this way, making all the methyl groups equivalent, but also then making these CH2s give the same product. So in this case, there would just be 2 products that are the unique products for this reaction. Okay. For the ethyl cyclohexane, we would have an product A, then the CH2 product B, and then the H in the tertiary position would give us product C. And then these two CH2 groups would give us the same product, which would be a 1-chloro-2-ethyl cyclohexane. So they would both be labeled as D, the fourth different product. Then these two CH2s here would give us the same product. If we put a chlorine here, it would be 1-chloro-3-methyl cyclohexane, and so they would be labeled as E's. And then finally the CH2 at the end that would give us 1-chloro-4-ethyl cyclohexane would be F. And so in this case we would get 6 unique products that are possible from this free radical halogenation reaction. Okay. So then for product 5, we have to predict the major products of the reaction. So we're going to start with this as our molecule. We're going to have a CH3, a CH2, a CH, a CH2, CH3, and another CH3. And so those will give us these products. So these two CH3s would give us product A. And again, there's kind of a symmetry here, making these two CH3s equivalent, then making these two CH2s equivalent. Finally, there's a CH, and then down here, this CH3 would be D because it's going to give us a unique product. So we'd have A, this to give us product B, product C, and then finally product D. So I've given you those 4 products, and so now the question is, what's the major product? And so what we do for each of the product is we take the number of hydrogens that gives us that product, and that comes from the original molecule times the selectivity of that position, where it's either a tertiary hydrogen, a secondary hydrogen, or a primary hydrogen that's being substituted for. Chlorination at room temperature is a selectivity of 5 to 3.4 to 1. So we're going to take the number of hydrogens times the selectivity. So if I color code these hydrogens, these two CH3s would give us product A. So how many hydrogens are there? 6. It's a primary carbon, primary hydrogen with a selectivity of 1. So that's 6 times 1, which is 6. For the B's, how many hydrogens are there that give product B? There are 4 total. So there's 4 hydrogens here. That's a secondary hydrogen, secondary carbon. So it's 4 times 3.4, which is 13.6. So that's our new leader. Then for the CH, it's its own 1 hydrogen. So that would have 1 hydrogen, and it would have a selectivity of 5 because it's tertiary. So that would give us 5. And then finally the CH3 at the end, which I'll just circle here. There are 3 hydrogens there, and that's a primary hydrogen, primary carbon. So it's 3 hydrogens times 1 for 3. So it's number of hydrogens times the selectivity. And in this case, ranking these from highest to lowest would be product B at a 13.6. Next would be product A at 6. Product C at 5. And then finally product D at 3. So that's how we would rank those products from highest to lowest. Okay, again, number of hydrogens times the selectivity. So now what I'm going to do is now I'm just going to change the reaction to bromination at room temperature. So again, I'm going to have my same molecule, my CH2CH3 attached to the CH and then that CH3. So A and B and C and then, of course, B and A, and then product that leads to product D. But in this case, for bromination at room temperature, the selectivities of tertiary to secondary to primary is 1700 to 80 to 1. And so now I'm again going to take the number of hydrogens times the selectivity, and that's going to give me the number. So again, same numbers as before. To give us product A, there's 6 hydrogens. To give us product B, there are 4 hydrogens. To give us product C, there is 1 hydrogen. And to give us product D, there's 3 hydrogens. In terms of product A, it's a primary, so primaries always have a selectivity of 1, as does product D, it's primary. B is secondary, so it's going to have an 80 selectivity, so it's going to give us a grand total of 320. Down here we have a 3 and a 6. And then finally that 1 hydrogen is attached to a tertiary carbon, C, and so that's going to give us 1700, as this is a tertiary hydrogen. This is a secondary, this is primary, and the CH3 is also primary. So in terms of numbers, product C is the big major product at 1700. Next is product B at 320. Then A at 6. And finally D at 3. So again, number of hydrogens times the selectivity of that hydrogen that's being replaced. Okay, and then for the final product, for the final reaction, same molecule. Only in this case, we still have A and B and the CHC. Only in this case, what I'm going to do now is I'm doing bromination or chlorination, either one at greater than 300 degrees Celsius. What happens there is that the tertiary to secondary to primary selectivities are now 1 to 1 to 1. So in other words, it's going to be, the product's going to be based totally on which hydrogen, which product comes from the most number of hydrogens. So it's pure statistics. So again, A is 6H. 4 hydrogens give us product B. 1 hydrogen gives us product C. And 3 hydrogens give us product D. Selectivities are all 1. Which means we've got 6 for A, 4 for B, 1 for C, and 3 for D. So the major product is A at 6. Next major is B at 4. D at 3. And C with 1. So again, taking the number of hydrogens and multiplying it by the selectivity. Okay, so that would be how we would do these problems, by calculating the number of hydrogens, give us the product, multiplying by the selectivity of that position, whether it's a primary or a secondary or tertiary. But what you've seen is that the conditions change the selectivities from bromination or chlorination at greater than 300 degrees would be 1 to 1 to 1 versus chlorination or versus bromination, which is 1700 to 80 to 1. And then finally chlorination, which is 5 to 3.4 to 1. So that's how we would do these problems to predict the major products of the reaction.